Hi, welcome back. So now we're going to take a look at a block on a table, but we're going to add friction. And we're going to use the 5 steps again. So let's get right to it. So what we'll do here is we'll add a block on a table, and we'll say it's a mass M. And let's even throw in a force that's applied, and we'll make it at an angle theta with respect to the horizontal. That good? Okay, but we're also going to add friction. So if you have a friction problem in a book, they're going to probably give you a coefficient of friction unless you have to solve for the coefficient of friction. But for here, let's just say that we're trying to find the acceleration of the system. So you have a block with an applied force being applied to it, and it's on a frictional, it has a surface with friction, and we want to solve for the acceleration. So guess what? The 5 steps. Step 1, choose a coordinate system. So the simple coordinate system would be to choose an XY axis or a Cartesian coordinate system. Step 2 is identify your forces. So how many forces do we have? Just look at what's touching the object and then add gravity. So you see that there's an applied force, so that's 1. You see that there's normal force, I'll get to gravity last. You have the normal force, which is the force, the contact force of the ground pushing up on the object. Then you know that there's friction, and friction would be in the opposite direction of the object's motion. So there's friction, and then gravity. So you see we have 4 components of force, or should I say 4 forces. Now, one of those forces has 2 components. As you can see, that's the force applied. It has an X component and a Y component, meaning it has a part of the force that's going up, it has a part of the force that's going over. So we'll end up having to resolve that. But guess what? That gets to step 3. So now that we've done step 1, we chose a coordinate system, and step 2, we identified our forces. Step 3 is we break our forces into their X and Y components. So let's just start our equations. So the sum of the forces in the X acting on the block would be equal to the force applied However, since it has a component, we realize that the X component of that force, which I'll highlight for you right here, that would be F applied sub X, meaning the part of the force that's moving to the right. So to resolve that, you would multiply it times cosine theta. If the arrow's pointing to the right or in the positive X direction, it'll be a positive force. If the force is pointing towards the left or the negative X direction, you make it negative. Well, the frictional force is in the negative X direction, so we say minus the force of friction, and that equals ma, where m represents the mass of the object. So now let's do those forces in the y. So the sum of the forces in the y direction would be the normal force, since it's pointing up. Now, how do you know what forces to put in this equation? Well, any arrows that are pointing up, that's a positive force. Any forces pointing down, that's a negative force. So the normal force is pointing up, and then the y component of the force applied is pointing up, and that would be side opposite of what looks like a right triangle. So therefore, you know that that's going to be plus the force applied times sine theta. And then you have what's going in the negative x, gravity. So that's minus mg. Now the interesting thing about the y direction is we don't have to say it's equal to ma. We know it's equal to ma. However, it's ma in the y direction, meaning the acceleration in the y direction. But since we see that the block is not leaving the table, it's not falling through the table, then we know the acceleration along the y-axis is 0. So we can just go ahead and call that 0. Now why is that important? Because it's going to play a role in how we define the frictional force. But we'll get to that in a second. So what I'm going to do is I'm going to solve this for the normal force. So I would bring this over, which would mean I would subtract force applied sine theta from each side, and I would add mg. So this would become mg minus force applied sine theta. I always like to have my positive terms in the front. So now that you know that, why do we need this normal force? Because if you look at how you define the frictional force, the force of friction is equal to the coefficient of friction times the normal force. So if we substitute this in for the normal force, this would be the coefficient of friction times mg minus force applied sine theta. So now we can substitute that in for our force of friction. So I'm just going to put a semicolon here to separate, and we can say now the force applied cosine theta minus mu, and we're going to substitute for the frictional force, so that becomes mu times mg minus F applied sine theta. And that equals ma. So we're almost ready. We needed to solve for the acceleration, or the equation of motion of the system. So we're going to solve for the acceleration. And that would mean that this eventually becomes the acceleration is equal to force applied cosine theta minus mu mg minus F applied sine theta all over m. Because we took the mass and divided both sides by m. Now some people might be tempted to try to cancel out this m. But in doing that canceling, it wouldn't cancel out the mass throughout the entire equation. It would only cancel out the mass in this term. So for practical sake, if you're solving for a number, just go ahead and leave it in this form. Now you can plug in your values and solve for the acceleration. Notice, like before I say, the best thing you can do is not plug in any numbers until you get to the end of the problem. It'll save time, it'll help you keep from making mistakes, and it's a much more efficient way to solve the physics problem. So that is how we address having friction. Now the one last thing that I want to point out, if you don't have friction in your problem and you're doing one of these Newton laws problems like a block on a plane, you don't have to worry about the y component of the force so much, because you can solve this equation if there's no friction without having to put in the y component, because the y component factors into the magnitude of the friction. But if you have friction, then you're going to need the y component to solve these type of problems. Well, if you have any questions, just play the video back and see if you can solve the problem without my help. Set it up like this, and then just go through the steps. If you start to get stuck, start the video again to give yourself a little bit of a hint, pause it again, and finish out the problem.